in principle, we are recording. And so, as you can see here, after a first glance that we're giving today to the topics, I'm going to use the Tohoku event, March 2011, to show to you some phenomena that are very interesting to us. Not only about wave propagation, but wave generation. Then we're going to spend one lecture about what can be called dynamics. That's again ridiculous. Then we're going to spend a terrible lecture on representation theorem. It's the basic tool to take a fault with a shear dislocation on it, that's the source, okay, with a complex kinematic process, and we're going to represent it with a set of body forces. You could ask, why? Please do.
Why?
Why? Because we have no other way to solve the equations of motion. You cannot solve the equation of motion with a discontinuity. You cannot do algebra. But what we can do is to remove the fault and the slip on it and replace it with a distribution of body forces. It's a fake, but it's perfect to describe the propagation of waves. So the pattern of radiation by a realistic fault can be obtained using a set of body forces. And when you squeeze everything into the simplest body force that you can imagine, that will be a double couple, then we're going to study also what we call focal mechanisms, okay, the beach balls. But the starting point will be what I call the representation theorem. Well, I don't call it, it's the representation theorem. Then we're going to spend a lecture about the Green's function, starting from simple examples, like, well, the simplest one maybe is the acoustic problem, because we have just conventional waves. We have a fluid, like air, and it's the scalar version of something that is much more complicated for solids, because we have directions. So pressure is not enough, as you know. We have to use stress and strain. And the Green's function is more complicated, because the answer of the medium will depend on the direction of the force. So if you're pushing along this direction, the answer, the sound, will be different. Using those two concepts that are coupled in some way, we're going to spend a lecture about focal mechanisms. So the beach balls, we will try to understand why they are so nice and simple. And in the final part, we're going to devote some time to an extended. We will go back to an extended source, and we will study what is called the source spectrum. And that's really important to understand what is the Moder magnitude, that is called MW. We will spend some slides about the history of magnitude, if you want, the original one, the Richter one, then the instrumental ones, MS and MB, and we will try to understand why the Moder magnitude is called MW, and it's based on seismic moment. And that's the lecture about earthquake size. Then the last terrible lecture will be about Q. You remember Q? Well, if you don't, I will go to Patrizia, but Patrizia is not here, so you're lucky. We'll take your grades in wave physics.
Power factor.
Pardon?
Power factor.
Quality factor.
Quality factor.
Quality factor. We have been studying the quality factor of a very simple system that was the harmonic damped oscillator. We will try to understand what is the Q of the Earth, because it's not perfectly elastic. Definitely it's not. And to understand an elasticity, we will need to use some viscoelastic models. So we will enter just a little bit in some rheology problems, just to get a part that is dealing with viscosity. We need it. We need it on short time scales. Short time scales is the time scale about wave propagation in the Earth. Do you remember how much time it takes for a wave? I'm looking at you, I'm sorry. For seismic waves to travel across the Earth? Do you remember the lecture about the three modes of the Earth?
Yes.
Should I call Patrizia? Okay, well, we have a picture today. Let's say they are taking 1 hour and a half to cover, to make a round of the Earth, half a round of the Earth. It's really a short time scale. It could be long, but for geodynamics, it's really short. Well, on these short time scales, the Earth is behaving as a viscoelastic solid, because part of the energy is lost there during propagation. The same concept of viscoelasticity can be used on much longer time scales when you study the deformation of the Earth on 1 million years, okay? And rocks can flow, and you can create the beautiful mountains that we have here and many other parts of the globe. And the end of the story, I hope, is about just a little bit of tsunami physics. It is a gravity wave. It's a long period gravity wave, and about hazard as a general concept. Part of these topics will be covered in the other course given by Stefano Parolari later in this term. It is called Applied Seismology, as far as I remember. But you're going to study with Stefano site effects, for example, and some other effects more related to seismic hazard. So I will give to you just a glance of hazard concepts. And that's it. That's supposed to be the end of the story. So, 2 of you can access this website. I fear that you can't. In principle, it's free, but to enter into the Moodle of ICTP, I guess that you need an ICTP account. Have you tried to? Maybe you tried.
No.
You didn't.
Yeah.
You tried.
Sì, quando mi ha inviato il link io sono riuscita a accedere.
Quello di UNITS però. Sorry for the Italian, you're going to learn some Italian.
Yes, we have to learn.
No, you don't have to, but...
Forse sì, però sono riuscita a accedere.
Okay. I can send to you an email. Oh, okay, just I'm asking you a favor. If you, for those of you who are going to attend this course, can you send to me an email so that I can create a sort of a mailing list if I need to send to you some additional material, like it's here, it's embedded here, or some communication, I don't know. So I'm asking you, you know my email? If you don't, it's Romanelli with 1 L at, I think all of you know my email, maybe you don't. Okay, that's at units.it, that's the official. I have also the ICTP account in case, but please, for those of you that are going to attend this course, please send me an email, okay, so we can create a mailing list. Okay, any other general question about why we are here? I don't know, actually. I'm sorry for you because let me show to you, John. I want to impress you. Well, let's use this one. It's starting in a nice way with a beautiful picture about Leon Nopov, who was one of the most famous seismologists in the world. He passed away just a few years ago. It was great. He gave a lot of lectures here at ICTP, and he was one of the authors of the representational theorem. Well, that's the end of a nice part of the story, because the bad part of the story is like this, or like, that's still nice. That's it. Okay? We will try to understand what we do have here. No way out if we want to understand why a double couple, why a couple and double, and why a moment. Okay? The time schedule of this course, I think you know it. It's on WED and Friday from 11 to 12 past 12. Today we'll try to be sharp. Usually I'm grabbing from you additional 5 minutes, but today I have to collect some persons at the airport. And once I'm going to receive your email, I will try to post this website, but I guess that you will not be able to access, so we'll create a sort of an archive, but I did it for you.
Yes.
Of the other course?
Yes.
Okay.
It worked. I don't remember how, it was like
Wave
Some
physics.
kind of like, yeah, I don't remember the platform you used, but it worked.
No platform, because actually I could save this in a Moodle platform and transfer it to the UnityS platform, but then I would have to ask to someone to create a new course, and that's a mess. I will try. In the worst case, you're going to receive the huge pack of the PDFs.
Oh, okay. I mean, like, I didn't have to log in anywhere. It was just like downloading the file
That was,
for me.
yes, that was an easy solution, but not an elegant solution.
Yeah.
The elegant solution would be to recreate this one
Yeah.
into parts of, actually, many of these lectures are also on the Moodle UnityS website, but the courses are rearranged in a different way. So I prefer to make some clean parts. So, before starting with the introduction,
Oh, I have a question.
yes,
Okay. So, like, the official finishing of this course is like
after 12 lectures.
after 12. It's an exam, right? No, there is exam.
Yes,
There is exam.
there
Okay.
is an exam.
It's
Bad news. Bad news for you.
good news.
Have you been practicing with oral exams?
Oh, just
Yes.
Oh, yes.
Oh, so you did it. If you passed with Karim, that's fine. Okay. Karim is much more a bad guy than me. Okay, yes, there will be an exam for UnityS rules. There is no grading, I guess. Just it's binary.
Okay.
Usually, most of the people know that I'm very good. What I'm going to, it will be an oral exam. And in the last 10 years, yes, the exam was just a sort of a colloquium about the topics that we cover during the course, asking to you all the algebraic passages. No, I'm joking. So just, it will be a sort of a colloquium with a tour, a logic tour about the topics that we covered, okay? It will be at the end. I will manage with Patrizia the official date, but okay, don't worry. It will be a sort of informal. It's not a written exam, so no staying here with writing
so
things.
like
It will be an oral. Pardon?
Individual scheduling.
Yes,
Okay.
yes.
Like a presentation.
No, a colloquium, a chit chat, okay?
Okay. Okay, well, we also.
For example, tell me what is the source spectrum, seismic source spectrum. Then you start to draw, and then I'm going to interrupt you.
With everybody here or individual?
Look, in Italy, but I think everywhere, the exams are open.
Okay.
So in principle, the door is open. In practice, most of you, in the last years, asked all the people to go out and close the door. But in principle, it's open. So it's up to you. I don't care.
I have another question.
Yes.
Do you have like additional literature you recommend for this course?
Yes, there should be. I prepared a syllabus with. Okay, let me tell you. Let me answer in a different way. No, first, let me try to open the. Okay. There is only. Oh, it's like that. Okay. Okay, that's not the answer. It's just the opening of the file for today. The answer is yes and no. The answer is yes, because the best book, you see, it's a simple course. That's Tsunamis. If I'm going to this one, that is the wave physics, there was a syllabus at the end where I was suggesting some readings about the topics that we covered during the wave physics course. But actually, it was about seismic waves. The best book, that's my opinion, I'm not getting any money from selling this book or buying this book, it's this one. It's very famous. I think I have already given to you, for example. I've already given to
No,
you.
I mean, yeah,
But my course is so hectic that I'm jumping with a personal logic. But this is containing most of the course, and you have already used it. There is another book that is containing what is not here and that you're going to look in my slides. It's a beautiful but a terrible book. It's called Anarchy and Richards. It's called Quantitative Seismology. Actually, it's not quantitative, it's pure formula. But I'm not asking you okay. Okay, this expression will be in one of my slides. The only place, the only book on earth that is containing all the theory that I'm going to skip many parts of this, is in this book here, as you can see. That's the title of the book. Actually, I guess that half of the seismologists in the world never touched it because it's very difficult. But it's beautiful. So any theoretical doubt that you can have, the answer is here about classical theoretical seismology. So my answer to you is, okay, all the additional material that we're going to discuss is already included in those. I'm going to use some videos from YouTube, very nice, very funny. But all the material that I'm going to ask you is in my slides. Of course, you have plenty of books that are covering these topics. In some parts I'm using Steiner and West session. In some parts I'm using Aki and Richards. But this is really a difficult book. So what I'm going to do is to grab some of the most important formulas, the most important concepts. And so, in my opinion, the most important thing is logic, not algebra. Of course, you can learn it from the first page to the last. But I'm not asking you to do this, but it's the book, okay? Okay, so trying to answer why we are here, and I don't have an answer, and probably you will never get an answer also from me. The real question that we are going to try to answer is this. Apparently, it's a very simple question. In practice and in theory, it's a really difficult one. That's the old Japanese answer. And maybe it's still valid for some ways. But Tsunamis, Kashima is the god that is trying to keep it in a relaxed. But as soon as Kashima, that is here, is distracted, the catfish is moving. And earthquakes and tsunamis are occurring. And in the Japanese tradition, also the modern, contemporary culture of Japan, earthquakes and tsunami are everywhere, as you can imagine. And I think that that Japan is the best, is the country that is more advanced in trying to reduce risk, seismic and tsunami risk. Risk is not hazard. Hazard cannot be diminished, can be assessed, but not diminished. Risk, that is the convolution of hazard with at least a vulnerability, can be diminished, working on vulnerability. And until 2011, Japan was supposed to be the strongest country in the defense from earthquakes and tsunamis. Well, maybe you do remember what occurred on March, and it was terrible. So we learned a lot of lectures from that event. That's why in this introduction I'm going to use some snapshots from different data coming from that terrible and beautiful event, trying to show to you some of the features that we're going to cover during this course. But okay, some of you definitely can answer much better than myself to this question, because the answer is, okay, fluid dynamics. That's the answer. But on very large and long time scales. Why do earthquakes happen? Because we have dynamics. And so this beautiful animation of the interior of the Earth, that is actually, it's a movie. We don't know what's occurring there. And maybe we will never know. But if you use Navier-Stokes equations, and if you model the Earth in a sort of a realistic way, you do understand that we have dynamics. And we have rheology. And rheology means the study of the deformation and the reaction to deformation on different time scales. The point of view of seismology is very limited because it's considering, let's say, hours, maybe days. That's nothing. It's a snapshot compared to millions of years, as you can see here. So the real answer is in fluid dynamics. Fluid dynamics. Fluid, that's not fluid, right? You can hear the acoustic, you can measure, we can measure with the accelerometer here. Is it fluid? Oh, yes, it is. Because if I stay here for 20 years, I will, okay, I'm already old, but okay, it's going to be deformed in some way, especially if you apply the weight. For example, if you drive a car on the tar, it's solid. But if you are in a beautiful summer day, and if you put a heavy weight on the tar and you wait, it's going to be deformed. If you have a heavy motorcycle, like my old one, you will discover that tar can deform in a plastic way. So it's a solid, yes, on very short time scales. On long time scales, most of the Earth is fluid. Well, the outer core is fluid, okay, it's a beautiful, pretty much perfect fluid. But also the lithosphere can be considered a fluid if you wait a long time. The asthenosphere is fluid. But S waves are traveling, so it's a paradox. The answer is in time scales. So the real answer to why do earthquakes happen is because we need to study fluid dynamics. But I'm a poor seismologist, so we're going to study that's another model. Yeah, you can do many things here with, according to the layering of interior of the Earth. Still, we don't know what's occurring there, which kind of convection dynamics are there. We don't know. We can produce models, but that's the answer. Our answer will be different because we need to, in this course, especially we're going to study the kinematics of a seismic source. Also, if we are going to give a look to the dynamics. Now, using very nice cartoons that I downloaded from the IRIS website, this fluid dynamics is revealing the interaction between the asthenosphere and the lithosphere, so rigid and plastic if you want. We have different dynamics. I'm not a geologist, definitely I'm not, but we know that according to the regime of stress, we may have divergent zones, we may have convergent zones, where the lithosphere, and if you want tectonics, is acting. And it's accumulating stress. So you will see, maybe on wet, that a very simple model that is reproducing in some way this is to use a brick on a plane, but the plane needs to have some friction. When you want to pull the brick, there will be a moment in which no reaction. And there is a game between the pulling force, could be tectonics, and the friction force. So we're going to accumulate stress there. It's an energy balance. Force, stress, normal and shear. Okay, when the stress is winning over friction, slip, stick slip. If you play violin, you're using exactly the same principle on very different time scales. If you use a bow and the string of the violin, because actually you're using stick and slip, but many times at a second. So friction and elastic forces, that's the game. And when stress is winning over friction, slip. It's a sort of a sudden slip. Okay, so if you want, that's the answer. And one of the simplest answers was given in after the 1906 San Francisco earthquake by Wright, who created the theory of elastic rebound. So you can also imagine to take two combs. I don't use combs, as you can imagine, but you can imagine to put them together and to pull them. At a given, if you pull enough, then you will create some sound, okay? Or like a musical box, when you turn it, okay? Sooner or later, some sounds will be created. Okay, on the scale of a fault, that's the typical example of a strike slip fault. Well, this is what's going to happen. And we will have a sort of a sudden release of energy. That's an earthquake. And of course, you may have many additional manifestations that can occur before and after an event. And that's why one of the most, how to say, nice and deep visions of the physics of the earthquakes actually is coming from modern geodesy, if you use a GPS, like in this case here. You can study what is called the seismic cycle. So you can study what is occurring suddenly after the release of energy. You can study what's occurring, okay, let's say immediately with the release of energy. It can be called the co-seismic part. Then you can study how the stress is released in the days, years after an event. You can call it post-seismic event. And then you can also try to understand how the stress is going to recharge. And so you have a vision of the seismic cycle. The most important tool to study these features now is to use GPS. So that's why in this last cartoon here, that's important, because in a subduction zone you can have a vision of the accumulation of stress, the release of stress, and what is left on the ground in terms of ecoseismic slip. I think you already attended the Alessandra Borghi course.
No.
Borghi's course? It's going to start in these days? Yes.
Let's do this.
Okay. With Alessandra, you're going to study, part of the course is devoted to GPS and geodetic measurements. Well, actually, part of the theory that she's using is coming from a terrible lecture that we are going to spend about the Green's function. There will be a nice surprise there about the co-seismic slip. So that's why I was leaving here this nice cartoon. Okay, what's next? That's an earthquake. So you have a brick with its own normal weight, you have a pulling force, and you have friction. Now let's imagine to know all the actors here. The pulling hand, the weight of a brick, and the distribution of, let's call, asperities on the floor. Then you can imagine that everything is known and constant. Then, in principle, we can draw this line here. So you have a stick regime and a slip one, stick and slip, like a violin player. And in principle, what you can get from this plot here is the duration of the accumulation of stress. So this part, and in principle, you can know what is the amount of slip after the stress is winning over friction. So that's the slip on the fault. Let me tell you one thing. The most important quantity that we're going to study in this course is really simple. It's the simplest one. I'm going to use the same symbols that we are going to use in the representation of your lecture. That's seismic moment. Now, I know my writing is terrible. That's the Greek mu. It's rigidity modulus. We studied in the wave physics course. Did we?
Yes, we did.
And what is a rigidity modulus? Please, I'm using you, but you know that I'm joking. Do you remember what is rigidity modulus? Yes, you do. You don't? Think.
Property of the material that what much it is rigid.
Okay. We all know Hooke's law. Thanks, Robert. That's too slow. You know, we're at a PhD course, so we're not supposed to write everything. That's too slow. If you couple with Newton's second law, and you know that they were not friends, you can create the dynamics of an harmonic oscillator. Good. Then, to describe a solid, that's not enough. We need to replace the force with stress. We need to replace the displacement from equilibrium with strain. And we need to replace K with 81 quantities. Oh my lord, no. Not 81 because we can use symmetry principles, energy conservation principles, and we're left with 21 quantities. Oh, good lord. But for lazy people, we can assume that the body that we're considering is isotropic, and we're left with two elastic constants, lambda and mu. They are called Lamé parameters. Lamé is French, it was not entering in the game between Hooke and Newton. Lambda and mu. One is deeply connected with compression. Because for a pure fluid, I'm trying to recap some ideas that we studied during the wave physics course. So we have two. This is going to be described by two elastic constants. And this has a name. This is called rigidity modulus. This has not a name, but if we consider a pure fluid, the rigidity modulus is 0. And lambda is called bulk modulus. And it's sound. Good. If we consider a solid, we have that Vp and Vs. So the velocity of P waves and S waves are related for an isotropic medium to lambda and mu. Do you want to take a pure fluid? That's going to 0, and this is going to be the sound velocity. Good, it's a recap. Now, what is the key point here is that lambda is related to compression. Mu is rigidity modulus, and it is the ratio between the shear stress and the shear strain. Now, for an ideal fluid, we have no shear strains. And so mu is nothing. And we're left with sound waves. But for a solid, mu is telling us how a solid is reacting to shear. And a tectonic earthquake, in a very few words, is a shear dislocation of a fault. Like that. Of course, if you are dealing with volcanic events, we have also an explosive component. So that's not the end of the story. But for pure pure tectonic events, the game that is played is something similar to that one. We have a normal force, the weight, friction, and shear force. That's why, for pure tectonic events, in the definition of a seismic moment, that's mu, rigidity modulus. Now, and that's a question for you, what are the units of mu?
Newton per meter square.
Why? Good.
Because it's equivalent to the stress dimension.
So, stress, strain is a tensor made by pure numbers. Stress has the units of Pascal, if you want, better bar, if you want to deal with the Earth. So this has the dimensions of Newton over square meters. What is this? Well, that's the area where the rupture is occurring. There is just chaotically anticipating. Let's imagine this is the fault. we have a point where nucleation is starting, rupture is propagating, end of the earthquake. That's A. At the first approximation, it's the length times the width of a fault. Good, it's an area. Now wait a second. Newton over square meters times square meters. What is this? Well, that's the average of a slip vector on the fault. So it's the average slip. So it's a length. So the units of this stuff here is Newton times meter. It's a moment. It's the definition of a moment. Actually, Newton times meters is also an energy. It's a joule, right? Yeah. But in this version here, the physical meaning is Newton times meters. Well, that's the end of the story for the representation theory. You cannot relax. We're going to conquer this, maybe. What I'm telling to you is that this is the most important quantity to describe, at the first glance, a seismic source. It's called a seismic moment. And this quantity here is entering into the new, well, new. It's old as punk because it was created in 1977. It's MW. So that quantity is entering the modern definition of magnitude. That's why I'm telling you why it is so important. And the most important thing to understand physically is that here we have rigidity modulus, because it's shear. Okay? Times an area, times a displacement. That's why it's called a moment. I know this is a violent recap of something that we already discussed. All of you know VP, VS, something like that? It's a real question. Do you feel confident with VP and VS or? No. Bad news. Because this course is starting from the wave physics course that was given in the first term. By the way, okay, we will try to do our best. Next. What about you, VP and VS? You feel confident with them? Okay. So by the way, this quantity here is the slip. In this very simple model, it's how much the brick is moving. It's the slip. So, with this model, we know everything. We know when and how much the slip will occur. Game over? No. Of course, no. Because it's very easy to complicate this system here, like with this system here. Two bricks, yeah. Let me stop it. Otherwise,
the MW is related to the moment?
Yes, but we have to wait some lectures to understand how. Oh. Well, actually, just a pure number and the logarithm. But M0 is entering into the definition of moment magnitude. That's why it's called moment magnitude. You can ask why W? Well, Kanamori said that it was the first letter that was available after P, S, L, and other things. But there is a nice way to remember it, because if you want, W can be also be understood as work. And work is something similar to Newton times meters. Okay. But yes, that's moment magnitude, seismic moment, moment magnitude. But it's just a prequel. So, okay, if you give a look to this system here, now it's chaotic. And you cannot predict when and how much the blue slip and the red slip will occur. So actually, we have to understand in a very simple way, but Karim's course will cover better with this part, that the seismic cycle is not deterministic. So it's not easy to understand what's going on there. We know where, we know maybe how much in the future, but we don't know accurately when and how much. So that's the dynamic box where we should move, but we are going to give a look from the kinematic point of view. So the effects and not the causes. And that will be enough, trust me. Okay, don't worry, this is just to impress. Because if you want to spend some time about the theory of source dynamics, you can enter into theoretical physics. For example, with rate and state friction law. Don't worry, this is not part of the course, just to impress. In Karim's course, I guess you're going to spend some time with this. So there are some beautiful dynamic models trying to deal with fracture and friction at very small scales. And if you want to study, well, you do this, right? You can forget continuum mechanics at a given point and maybe enter into the microscopic and nanoscopic scale of fracture at atomic bomb scale. We will not do that. We will live in a beautiful continuum mechanics world. Okay? But, so this is just to impress you. Just to impress you is a very nice cartoon of an earthquake. No, it's not, but it's a possible representation. This is very nice. You see a plane that in the first approximation is a fault, where the stress imbalance is occurring. Let me try to show to you today. It's starting somewhere. I have to take this. So it's starting, nucleation, evolving, but stress. These are not waves. Oh, well, it's a wave, but it's a stress wave. Rupture is occurring, propagating, living, and in each moment, it's generating seismic waves. This is the music that we should try to understand. So that's a dynamic model. And of course, what you can do is to imagine that the orchestra of the players is made by different instruments. And so once a player is singing or playing a guitar or drumming something, stress is released. And one of the most important quantities that we're going to define, it will be simple, it's called stress drop. So stress is increasing, sleep is occurring, stress is bouncing down. That's stress drop. It's related to this. And once the stress is dropping somewhere, maybe it's getting larger in other places. But still a dynamic concept of stress redistribution before and after an event or a chain of events. But still a dynamic frame. Okay? It's not part of this course. So I'm going to show to you what we're not going to do. Nice. And what I'm going to show to you now is what we are going to do using as a sort of a skeleton of different topics what occurred in Tohoku region on the terrible day in March 2011. Just to understand, because it's the first time that some data have been collected from many different experimental perspectives. Seismic waves, yes, but also GPS. And we will see something that is going to be very important and that we are going to study with the Green's function theory. Okay, so let's start looking at this event here. We are in a very different part of the world. It's a beautiful part of the world and very active. It's very active. It's much more active than the Alpine belt, for example, the Apenninic belt. How can you measure that activity? Well, for example, with this. The relative displacement, and it's a fast one. Well, you could say 9 centimeters per year, it's nothing. Well, it's fast, because if you take the point of view of tens, hundreds, thousands of years, that quantity is going to be large. And that quantity is going to be accommodated into different slips on the fault. So it's a fast place. It's a very active place. And if you want to see a cartoon from the side, you see, well, maybe a simplistic cartoon, but you see a subduction. That's the dynamics. Dynamics is there. Okay, tectonic forces are the dynamics. That's the dynamic engine, no way out. We have friction. We have seismic coupling, and the violin is going to play. So the purpose of this course is trying to understand the music. Listening at the music produced by players, not to understand the soul of the players. That's dynamics. So we're going to focus on the kinematics. If you want to see an impressive manifestation of activity there, let me show to you these two animations here with different time scales. I'm going to show them to you again. Well, on the left, we have tens of years. On the right, we have tens of days. Let's try to get back to it. And well, what's left there is impressive. By the way, let's see if I can. Oh, it's not easy. Okay, you see, you start here from 73. And if I run this movie on, you see many patches that are switching on there. Many sounds played there. These are all seismic events. So you will see that in these tens of years, you will have many concerts. And many loud concerts, because magnitude of these events actually it was large. And you see patterns, that's the plot of seismicity in space and time. And I use this just to show to you how active a zone can be. This is very active. Many patches, many events with foreshocks. Okay. So from 73 to 11. September 20, for example, here. Now let's give a look to this one. That's a totally different time scale, if I'm able to. Now that's March 9. March 9, and then, okay, wow, one event occurred there. It was an event of with magnitude larger than 7. We'll try to understand what is magnitude, but let me tell you, in Europe, a magnitude 7 is huge. For Japan, it's not. It's a normal player. But the point is that a few days after, 2 days after, a big player occurred. You see that big balloon there? Okay. That's the main event of March 11. And then the stress was released, but locally there were many aftershocks. And some of them, you see, I cannot release my finger now, but you see, okay, here there was another balloon, that was an aftershock with a magnitude from 7 to 8. It's another big one, but it was not the main player, it was not the main shock. Okay, so it was just in front of the Fukushima power plant. Okay, what I'm telling to you, dynamics is revealing in seismic cycles over 1,000 tens days, tens of years and days. Now let's try to give a look to one event, okay? There it is. Oh, what is that? That's not so nice as an animation. It's not an animation. Well, okay, this is the simplest representation that you can give of a seismic event. You see these two plots here? Actually, as a short name, as a jargon, they are called beach balls. They are simply a distribution of colored, usually black and white, as you can see on the left, patterns. And very simple, very regular, very symmetric. Okay. At the middle of the course, we're going to study focal mechanisms, using the theory hope, we have been discovering until that lecture. And as a very simple representation, a seismic event is this or this. These are two catalogs, very famous one. On the left you have CMT, Centroid Moment Tensor. On the right you have USGS, that is the US Geological Survey. So they are a little bit different, but this information can be released, let's say, in less than 1 hour after the earthquake, recording seismic waves around the world. Now look, all that beautiful and terrific energy released by the main shock is squeezed into these two tables. And as you can see here, a keyword is appearing, moment tensor. It's the tensor version of that quantity there. And this is what we have to understand. And number station, what else? That's a tensor. Okay, MW, that quantity there. It's 9. Wow, it's impressive. Somewhere here you should have also M0. No, just 6 and 6. Just to tell to you that if you want to squeeze all the information in the simplest possible representation of a seismic event, there it is, a beach ball with a moment. Okay, it's a long way to go there. Something nicer. From now till the end, I'm going to show to you in a very chaotic way many snapshots of this event. Okay, what is this? Forget about the title for 1 second. Okay, that's the recording here, in one place along the coast of Japan, very near to Fukushima, of a GPS measurement. So something that you're going to study with Alessandra. And it's a displacement. What you notice here is that, okay, it's 0, the instrument is there, then something is occurring, and then, wait a second, the pen of the instrument is not going back. It's not going back to 0. It's possible. Well, that's the near field of a Green's function. It's a nice terminology that is over a pain concept that we're going to study. But the funny part of the story is that it is called co-seismic slip. So it's something that is occurring with the slip of a fault, with the release of energy in terms of seismic waves, but it is leaving the system out of equilibrium. It's not going back again. Okay? And so a GPS that is measuring the absolute position, in principle, of the receiver, it's noticing something, but then the receiver is not going back. It's tilted. It's a permanent deformation. Now, if you take the derivative of the signal here, of course, this will be 0 and this will be 0. So it's disappearing. But in the displacement, a permanent dislocation is left. In modern terminology, it's called co-seismic slip. And you can study them with GPS. Okay, and what is impressive is that if you collect this information from the many GPS stations that were deployed at the time in Japan, it was one of the richest networks of GPS, what you notice in terms of horizontal and vertical displacement is that this static co-seismic slip is huge. Please give a look to the numbers here, meters. And something was moving part of Japan permanently in that direction. Wow. Okay, co-seismic slip. It's nice, it's beautiful. It's a modern vision, let's say modern in the last 20 years, at least 20 years, maybe 30. 20 years vision of a seismic source, not using seismometers, not using accelerograms, but using GPS. It's an important part of the story. It will be related to the long, very long period radiation. Very long. So long it's infinite. And we're going to study it. Okay. Another vision of the same concept, GPS waveforms. Now give a look to them. Now it's not a continuous field. it's a selection of GPS measurements along the coast. Now give a look to them. 3 components. Please do remember that the seismic field, displacement, velocity, acceleration, is a vector. So it has 3 components. Usually north-south, east-west, and vertical. Now what do you notice here? Tell me. What is striking your attention here? I hope. Well, the dots inside Japan, no. Focus on these dots, focus on these signals here. You can use both the vertical or the horizontal one. Look at the last one, the bottom one. Look at the amplitudes, look at the units, please. These are centimeters. And so this one, for example, it has a permanent tilt of 6 meters, right? Okay, that's 80 meters, 1.8 meters, 1.4. Look at this. It has no permanent tilting, right? Actually, if you look into it, you can notice these beautiful wiggles here that you cannot notice here, but they are there. But they're tiny. So with this scale, you cannot notice those wiggles that you can notice here and here. Am I right? Yeah. Are you interpreting the same feature? Look at the amplitude. At 70 compared to 6 meters. Okay, 0.7 to 6. So it's much tinier. With the classical waveform vision, 0, transient, 0. Okay. And also here, maybe a little bit, you see, but just a tiny part of a static displacement. That's why, when we will study the Green's function, we will call that part near field.
Which one?
This one. The static displacement that is left there, but it's not here and not here because these receivers are more distant from the source, that part is called near field. So if you want the coseismic slip from the point of view of earthquake dynamics and of GPS, in the theoretical seismology is called near field effect. You will, I hope, understand why. It's a prequel. Okay? But it's important. Okay. And that's the final plot for coseismic slip. Beautiful and terrific arrows recorded by the Japanese GPS network. What you will notice here is that when you move, when you move far from the source, you see that these arrows are 0. That's why it's called near field. Compared to far field. Okay. Just to let your mind to remember this terminology. Okay, that's from GPS. Let's move with the vision of signals coming from that event. Okay. Let's try to move into the realm of classical seismology. Classical seismology is using seismometers. So something that is based historically on an inertial pendulum, measuring the transient, then going to 0, in the domain of displacement, velocity, acceleration. That's displacement. No, it's acceleration, sorry. You can notice from the units here. My message here is that nowadays the sampling rate of GPS is so fast, is so short, that you can compare it with a seismometer. You know, 20 years ago, the sampling rate of a GPS was maybe 1 sample per second. So you cannot record something that is more rapid than 1 hertz. You cannot, you don't see it. But nowadays the sampling is so fast, is so short, that you can easily use it to understand some relatively high frequencies. So you see here the comparison of the signal coming from a GPS and the signal coming from an accelerometer filtered. But you see, they're pretty much the same.
What is cheaper?
I don't know. I don't know, that's a good question. Oh, well, Do you want an accelerometer?
Ah,
I think
that's-
all of us have one, right? So, how to say, an everyday accelerometer is very, very cheap. I think every car has it in the airbags. Every smartphone has it for every rigid disk, not SSD, computer has it because it was sensitive to falling, so stopping the engine. So a normal accelerometer is very cheap. A professional one is not. For example, for building monitoring, you can use also $10 accelerometers, but if you want to record slow motion, I think it's 1,000. So it depends. I don't know. I'm using some instruments, but I'm not an instrumental seismologist. So I don't know what is the cost. You can ask to Alessandra. What is the cost of a GPS? 20 years ago, I remember Karim was buying one of them for an old project. It was very expensive. But I think a GPS is nothing. But of course, a permanent station or a campaign station could be, let's say, 1,000. I don't know. I'm showing to you these pictures, just trying to understand the different visions that one can have of an earthquake using different signals. So GPS, accelerometers, but wait, because if you use the accelerometric Japanese network, and they have two, one is called KickNet, for example, you can see many beautiful pictures. Now let me show to you again this. Wait a second. Look on the legend. You see T, that stands for period, is now considering the band between 50 and 100 seconds. Can you guess what is the domain of seismology for periods? You should know the longest. 3 modes of the Earth. Come on, guys. You study. Are you the same person studying wave physics?
Yeah.
Yes.
If not, you are very similar to them. But do you remember the longest vibration of the Earth? Do you know? If you go to Borgo Grotta, you can study it with the giant pendulum. It's 54 minutes. So let's say some thousands of seconds. That's the longest period that you can imagine of vibration of the Earth. It's S02. You don't remember. Really, you don't. Okay, now, on the other side, if you want to deal with engineering seismology, and if you want to study buildings, you can go up to 10 or 20 hertz. So, very short period compared to the thousands. Classical seismology is between 1 and 100 seconds, teleseismic waves, if you want. Just to tell you that this is the vision of, let's call it, long period classical seismology. So the signals are filtered between 50 and 100 seconds. Let's say 1 minute. Now let's give a look to it. Look at the patterns. You see the wavefronts? And you have a first estimation of lambda, the wavelength. Let's try to give it to it again. Look. Here it is clear. Look at the difference between the blue and the red. You see it's hundreds of kilometers. Remember, once you have a period, let's take for example 100 seconds, it takes no time to have a first glance of wavelength. 100 times 4 kilometers per second, that is a typical seismic velocity, it makes 400 kilometers. That's a very long wavelength, but that's seismology. 400 kilometers, and you can see it here. Of course, if you go to shorter periods, you should have smaller wavelengths. Now, let me stop it. Let's give a look to the other cartoon on the left. Now period is shorter. You see, between 20 and 50 seconds. Now, if you take again 4 kilometers per second, now the largest wavelength will be 80 kilometers. Now, let's try to give a look to this one. Look. Let me try to go to the same. Okay, look. I never did this, but I did it. Okay, look at the two plots. It's the same snapshot. Remember, a wave field can be mapped using time and space. We should use both. But this is a picture of Japan at this time here, okay, with seismic waves that have been frozen there. Look at the difference between these two plots. Look at the distance between large red and large blue, okay? Look at the distance. You see that the wavelength in the left is much shorter. And you notice one other thing here. It's shorter, and look at the pattern. It's much more irregular. While here, you can easily trace, as you can see here, the wavefronts. They are spherical, cylindrical wavefronts. You see, this one is, at the first approximation, but you see why smaller scale wavelengths are more sensitive to heterogeneities. And if you decrease the period, you will be sensitive to smaller scale heterogeneities, and the wave field will be a mess, or much more messy than these ones. Okay, just to tell you that if you want, going from GPS to the seismic wave field, the classical one, it's like to make a travel from long periods, very long, because a static displacement is infinite period, okay, to shorter periods, 100 seconds. Can you imagine what's going to happen if you go to shorter periods? Well, let's first give a look to the duration of motion here. That's another important feature that is important also for seismic hazard. This is a beautiful animation at the Japanese scale, Japanese set of islands, of course, let's say 1,000 kilometers of the duration of the motion. Let's give a look to it again. Okay, starting. You see the shaking is starting in the nearest part. Now it's increasing. Look at the seconds. Now 1 minute has passed. Okay, it's propagating, it's going. Look, please give a look to this part here. It is nearer to the Tokyo Bay. And you see that it is flat. It's not hilly. It's not near the Fuji mountain. Okay. And it's a place where we have a lot of sediments on a larger scale. And this means amplification and longer duration. That's why you will see that when the waves will be passing here, and we will propagate out of Japan to reach all the rest of the world, you will see that in that part, motion is still persisting. And I want you to notice the duration. Look, you see that it is still there in some parts. These are the sedimentary basins. And now 6 minutes passed. 6 minutes, it's nothing for the earthquake cycle, nothing for geodynamic people, but it's very long for motion, 6 minutes. Okay. So, time scales, periods and time scales. Now let's give a look to this. After the wave field has been passing there, what you can do is to create a map. Why I'm showing to you this? Well, because it's a representation of the passage of seismic waves that is very important for seismic hazard, for example. What is plotted here, using the recordings from the KNAT of PGD. Now you could ask, what is PGD? It's very simple. It's peak ground displacement. So you take your signal, your beautiful signal, you take the peak and you plot it. And you see how the largest values are concentrated here and here, and then decreasing. Well, decreasing, yes, we know why they are decreasing. Do we? You should. But I'm hopeless today. Do you remember why they should decrease? Up to now, we have just one factor that is diminishing. Please tell.
Exactly. Why should it decrease?
In amplitude.
Okay, because of the radius.
The radius of the Earth? No,
No,
but
not radius of the Earth.
it's R.
R.
What is R?
The spherical.
Geometric asperitic. Okay, now, let me draw another ridiculous formula. Okay, that's a plane harmonic wave. We spent 2 lectures in building it. I hope you do remember. Okay, it's a very simple way. With just one frequency, one wave number, velocity is omega over k. It's beautiful. It's like a light wave in vacuum. Okay, that's a plane wave. But any physical wave is not plane. For example, if you have a point source and you have a homogeneous infinite space, it has to be a spherical wave. And the spherical wave, to balance energy, to conserve energy, because the power of a source is fixed, it is the sun, the light, the woofer somewhere, it has to decrease as 1 over distance. You do remember now, okay? If you take spherical waves. So, because of course power is given, and as the wave field is propagating, of course, it has to be spread on larger surfaces. And for a sphere, it's going with the square of the radius. That's why amplitude, and the square of the amplitude is related to energy, has to be conserved. That's why it has to be as 1 over distance. What about cylindrical waves?
The square. The square.
Okay. For Rayleigh and love waves, we are decaying much less. By the way, that's why, on average, the amplitude of a motion is decreasing with distance. That's not the end of the story. There is another important factor here that is going to decrease amplitude on average. It will be related to inelasticity of the Earth, but you will need attenuation to discuss that. It's one of the lectures of the course. By the way, that's PGD, that stands for peak ground displacement. Now look at this map. And now look at this. Because they are beautiful, in my opinion. Now, 2 receivers along the coast of Japan. And the first signal is being recorded by KNet, the other one by KickNet, we don't care. Look at how beautiful the displacements are. Okay? Look at the units, centimeters, for example. That's half of a meter. Okay? It's a big shot. 0, 0, so we are not so near to the source. 0, 0. You see by these wiggles here, that's displacement. That's 1 meter. Okay? There is a building in Japan on the coast that has been severely affected by the tsunami. In the basement, it was a seismically isolated building. And there is a metal plate with a needle that is recording the elongation. And it's impressive because the needle was going something like that. Okay? So it's 1 meter. Okay. By the way, displacement. Now, displacement, please do remember that every time that we go to velocity and acceleration, we take a derivative. Right?
Yeah.
If you take a derivative respect to time, omega is getting out. So, going from displacement to velocity and acceleration, the signal is getting richer and richer of high frequencies. If any. Because if you move away from the source, attenuation will kill this. But okay, that's another story. Look how different accelerations are. They are much richer of high frequencies. Okay? You do notice this immediately. Please do remember the units. Now, in seismology, it's pretty much ubiquitous to use terrible units like centimeters per second. Okay, you can use meters per second square. But please do remember that if you work with engineers, there is another unit that is used, that is G. So let's say 10 meters per second square. Why? Because it's very easy for them to compare them with the weight of a building. Okay? So you can see unpolite units, centimeters per second square, SI units, meter per second square, or strange units like G. It's an acceleration. You notice the difference there. Now, let's give a look to how beautiful they are along the coast. Now, if you take this picture here and you go from the north to the south, you see a very lively set of signals. Look at these ones. They have clearly two packets arriving one and then some seconds later. Please give a look also to the time here. Okay, that's hundreds of seconds. While here we have only one. Here we have two, but they are more mixed. So you see how the seismic event was actually a complex one. It was not a point, it was a rupture on a big, very big fault. And actually, if you now plot PGA, that is one of the most important parameters used in seismic hazard, look at it. Now, it's very different than PGD. Look how regular is this. Look how patchy is this one. You notice some hotspots. It's decaying much faster, and you will understand why, I hope, studying Q. High frequencies are attenuated much more than long periods. And you see it's much more patchy here. You can call it a sort of a strong motion hazard map. And actually PGA is one of the parameters, the key parameters that was traditionally used in seismic hazard assessment. Just a glance about this. I love this picture because it's containing the record, recorded in Tsukidate city, with the largest peak ground acceleration in Japan for that event. If you give a look to this, you will see, that's another unit that is called, okay, it's 3G. Now 3G means 1G, it means that you can throw a stone with that acceleration, okay? It's 1G. When you throw something, it's 1G. You're overcoming 1G, okay? Now it's 3G. I will skip this part for now. We will go back to this in the last lecture of the course. It's 3G, so one could say, wow, it was a total destruction of that city. No, it was not. In Tsukidate, actually, I don't think, no, I will not put here the picture, it's in the other lecture. Pretty much nothing occurred. Just to tell you that acceleration can be very large in many signals, like this one. Look, 3G is one of the world records. But it's important at which period it's occurring. Because if you give a look to this signal here, you see that it is very short in time. Actually, this very large acceleration is occurring at very high frequencies. So if you're studying, if you're dealing with an MPP or some important relevant buildings where also the plants are important, some valves, some tiny details, that could be important. But for normal buildings, this is pretty much nothing in the sense that it's occurring at very high frequency. You can hear it. But actually, the building is not moving in its own skeleton. Small parts of it are moving. Actually, the most part of the damage in that city was occurring to very tiny objects. Okay, That was the extreme of high frequency motion. Now, if you move out of Japan, and if you give a look to this event recorded worldwide, that's the vision. You should remember this slide. But I don't trust you. Okay, it's a new slide. We discussed it when we were studying the three modes of the Earth, from progressive waves to standing waves. Okay, by the way, if you study the recordings of this event, going from Japan to the other side of the world, now you get a feeling on how much it takes in time to travel there. If you go from 0 to, let's say, 90, 1 hour and a half, the waves have been arriving on the other side of the world. And if the player is strong enough, they can turn again and reconvene there after a whole travel through the world, again in Japan. And that was the starting idea of the three modes of the Earth. Of course, if your player is not strong enough after one tour of the Earth, here it will be practically zero. So to excite the three modes of the Earth, you need a large sound, because it has to overcome geometrical spreading, anelasticity, and to have enough energy to interfere with itself. That was the concept from progressive waves to standing waves, if you do remember. Okay, what's next? The final slides for today, and this is what we would like to study in the rest of the course. Let's say sometime after the event, a couple of hours, waves have been recorded by worldwide networks. Recordings have been used, as you can see here. Some inverse problem has been started, and it was completed. And this was the first image of a slip on the fault for that event. It was not the best one, definitely, but it was the first. And now you have a vision of a seismic event that is not a point, definitely is not a point. If you give a look to this length here, it's more than 600 kilometers. It's more than, okay, 200 kilometers along deep. So it's a large event with a distribution of slip that is concentrated in some parts, and it's not maybe the largest where the rupture started, and it took 240 seconds to occur. That's a rupture. This is the picture that we want to understand during this course, the distribution of slip on the fault. If you take the average, you get this. If you take the area of the fault, you get this. If you take this picture, you will get a moment that will correspond to a magnitude 9. One of the largest earthquakes recorded by humans. The largest one is the 1960 Valdivia Earthquake in Chile. Estimated 9.5. Remember, magnitude is logarithmic, so 0.5 is quite a lot. And that's one of the best animation that I can show to you about that event. That's the rupture. After a few days, some days, 10 days, 1 month, a new vision of a source has been released, and there it is. It's the model of a rupture of that event. Okay, let's give a look to it until the end. And now let me go back. And please give a look to the time scale on the top. Now, it's starting, nucleation is starting. Slip is occurring. The largest slip is occurring now, at depth. Then it's trying to propagate. Then it's stopping. Okay. Now, if the event would stop there, the magnitude would be much less than 9. So that could be an event of magnitude 8 point something, but it was not stopping. That's the beautiful part of the dynamics, that is not my part. But then the rupture decided to continue again and to propagate to the south. with largest but at higher frequencies release of energy, propagating to the south, then becoming a single rupture, and then dying after 2 minutes. 2 minutes of rupture. Now this inversion has been made also using these signals. Now maybe you do understand why there were 2 packages there of energy, and here at the bottom there was just 1. So the rupture was very complex. Now, what we will do in this course, we'll try to understand the kinematics of the rupture and how the rupture can be manifesting in what we record there. Of course, the real problem is dynamic. So to understand why the rupture occurred in this way. But for that, you have to wait for Karim's course. So we will focus mainly on kinematics of the rupture, except on WED, when we're going to give a very tiny look to dynamics. Now, the last 2 animations, but I don't want to stop here. Other animations of ground motion recorded far away from Japan. Here we are in US, and you should remember this, but I'm hopeless now. This was the recording of a lava wave that would become a torsional mode long time after the event. Well, long time. Nothing compared to the seismic cycle, but okay. Look at the time. Here it was less than 1 hour later. Now let's go here, because you will see that after some time the wave is arriving on the other side, because the waves were traveling along this direction, turning and arriving in the other direction. Progressive waves interfering can create standing waves, the modes of the Earth. Okay. We spent a lecture at the end of the wave physics course. Final one. Beautiful and terrific. Tsunami. One vision, then I will go back. Now you should remember all the time scales that we consider until now. 2 minutes the rupture. 6 minutes the ground motion on the Japanese islands, right? 1 hour and a half to make a turning point on the other side of the Earth. Okay? Tsunamis. Look at the time scale here, that's minutes. So when the ground motion was passing away, it was directed to the other parts of the world, tsunamis were still in the middle of the ocean between the source region and the Japanese coast. Because only after, let's see, if you remember some of the videos that have been recorded there, let's say 40 minutes later. Okay, the first ones are arriving now in some parts of the coast, and now 45 in the Sendai basin, and then propagating and causing what you maybe have seen in many terrific videos there. Now, 45 minutes, the waves were far away, seismic ones. What about these ones? Well, these are gravity waves. And if you want to take one message home with one very simple expression, you can take this one. The average velocity of a gravity wave in shallow water is this. This is the acceleration of gravity. This is the thickness of the ocean. If you take an ocean of 4 kilometers, and if you take this as 10 meters per second squared, this is roughly 200 meters per second. So if you want, you can compare 0.2 with 4 kilometers per second. What is my message? That being a gravity wave in a 4 kilometers ocean, you are fast, but not that fast. So it's arriving later. You can take it positive. It's a simpler piece of physics that we will deal with just for one lecture. Formulas are a little bit easier on average than the ones for seismic waves. And gravity waves are slower. But of course, and so good news, because we have some time to act. 45 minutes for Japan. For European countries, it's nothing. For Italy, I cannot imagine what to do in 40 minutes. Can you imagine being at the beach? Okay, I'm joking, but as an Italian. Japan was supposed to be one of the best prepared, the best prepared nation in the world for tsunamis. With a huge cultural work beyond that since the early schools, with immense defenses that were there. But it was not working for this. That's why in the last lecture, when we're going to speak about a little bit of tsunami physics, I would like also to spend some words about hazard and risk. Well, what was wrong there was this. And not from the point of view of nature, but from the point of view of the hazard assessment. Because no one was waiting for a magnitude 9. They were waiting and prepared for magnitude 8 and maybe 8.5. In Europe, we cannot imagine 8.5. But in Japan, they can. But it was 9. And so, the average tsunami height, instead of being 10 meters, 10 meters. I cannot imagine 10 meters of tsunami height. But what occurred, the height that occurred was 20 meters. And that was the tragic part of the story. Okay, so I have to run to the airport now, but please send to me your emails. I will send to you the Moodle ICTP website, but I'm pretty much sure that it's not going to work for those of you who do not have an ICTP account. If that is the case, as I guess, I will prepare a sort of a box with all the files that you can find there. Today was just an introduction covering many pictures of some part of the physics that we're supposed to study. Bad news. Representation theorem, Green's function. But inside those forest of algebra, there will be M0, there will be MW, there will be coseismic displacement. Okay? So that's the hard side of the story that you're going to study maybe in other courses. Okay? So see you on WED, and okay, waiting for your email. Now I will switch to it just then in English. Voi avete bisogno di qualche firma per essere qua o no, giusto? No, solo alla fine l'esame. You don't need any official stuff to be here. You have just inserted, for example, this course in your...
Nel mio caso con te mi ero accordato che
sì.
Potevo solo attendere il corso.
Sì, quelli sono fatti, però tu avrai anche una lista di corsi, giusto?
Sì. Ho una lista dei corsi, poi
okay.
Dovremo inserire l'esame nel TOR, chiederò, ma serve solo che attenda il corso.
You have just a list of possible courses that you have to attend, as far as I remember.
Yes.
Right? Okay.
I assume so. But
I assume so.
but that's my first course that I'm attending, so.
So the first and the most terrible one.
That's important.
No, I don't think so. You're going to attend also the Stephanos course, right?
Yeah.
That's more important. It depends on which kind of feature you want to deepen.